Alright, here we're going to see the backside of 6.3. And what this is multiplying by conjugates. You might remember this back in chapter 5. There we had conjugates such as a plus square root of b would pair up with a minus square root of b. We also saw them as a plus bi, a minus bi. Now we won't be using imaginary in this chapter. But what conjugates are terms that when we multiply them by each other, we're going to get the second term to, we're going to get these radicals to go away for us. Now, scenarios where we'd want to do this is when we're rationalizing denominators. Scenarios we saw last week would have been some of where, we have a denominator and there's, 2x in there. And we saw that we'd rationalize it by multiplying by itself. Right, and we do that to the numerator as well. And then when we rationalize, and it could be cube roots and fourth roots, we did some of those too. And when we multiplied straight across, we were able to free the denominator from having any radicals in it. Now, what this section rather is going to be about is, well, what would we do if instead of it being just the square root of a 2x down there, but what would happen if I put a 5 plus, or any number plus in front of it? Now, when we multiply, the 5 would get distributed to that, and the square root would still be around. So what conjugates help us do is, if this was by chance over top of underneath a fraction, so this was a denominator, basically this conjugate section is what could we multiply by to get the square root to still go away. And the answer is more complicated now than just a square root of 3, because, if we think about just putting a square root of 3 here, yes, it would turn that into a 3, but then another square root of 3 would show back up when it multiplied by the 5. So that's what conjugates help us do, is take down situations like this. Now this one isn't in fraction form, and none of these here today are, but that's what that's getting us prepared to, is to take down situations like that. So the conjugate of this would be a 5 subtract square root of 3. Because the way that this models is if one's a plus square root of something, the other one needs to be a minus square root of something. And let's see why from the FOIL process. 5 times 5 is 25. 5 times negative square root of 3 is negative 5 square root of 3. Here we get a positive 5 square root of 3. And then here, positive times negative is negative. Square root of 3 times square root of 3 gives us square root of 9, which is just a 3. Now this is the key part of the conjugate work. The reason that conjugates work is because the square root of 3 times square root of 3 turned into a 3 over here, and then these middle terms will always be opposites, thus canceling out. So 25 subtract 3 would give us this final answer of 22. So that's what multiplying by a conjugate does, is it took something that had a square root in it, multiplied it by a term, bringing it back to a rational number. All right? And this will work even if you have the constants listed second. So let's explore on this one piece by piece. Square root of 3 square root of 2 times 3 square root of 2. Remember that the way that these work is you multiply the outside numbers, so 3 times 3 is 9. You multiply the inside numbers, so that would be a 4. We'll come back and finish that here in a minute. Then we'll get a plus 27 square root of 2. And then here, let me change colors. Here, you get a negative 27 square root of 2. Notice that those will eliminate. And then we get a subtract an 81. Now this piece here, square root of 4 is 2. 2 times 9 is 18. So this boils down to 18 subtract, or add, a negative 81, right, which takes us to a negative 63. Alright, and on these, if you ever want to double check these, you can always type in that original expression into your calculator with all the parentheses, all the square roots in there, and you should be able to verify that you get a negative 63 on that, unless I've made a mathematical mistake on the video here. Which might have you wondering, well then why would we ever bother folding it out by hand? Well, if you've done a bunch of these and you're very familiar with them, like you would be in pre-calculus when you do these all the time, multiplying it by hand might be faster, especially if you have the knowledge going in that these middle terms are going to cancel out anyways. You could then just focus on 2 of the FOIL pieces instead of all 4. So it ends up being faster than typing it all in on your calculator if you find yourself doing these often. Alright, so this one has square roots all over the place. But it's just getting us to practice. A lot of this chapter has just been, not tied to any word problems, but it's just had us dealing with square roots in different scenarios. So let's multiply these out. 2 square root of 7 times 2 square root of 7 will give us 4 square root of 49. We'll come back for that. Then we'll get to subtract 6. Now remember, we're multiplying here, so those radicands on the inside will multiply. Here we'll get a positive 6 square root of 21. Then ending with a negative 9 square root of 9. That came from the 2 3s on the outside multiplying, the radicands multiplying to get the 9. Those cancel. That's 4 times 7 for a 28. That's negative 9 times 3, which is a negative 27. This gives us a value of 1. Alright, now, once again, you could type that whole original expression into your calculator, and you should be able to verify that you do, in fact, get the answer of 1. Alright, so here's one that actually might be tied back to a word problem scenario. So it says, this design here is made of small squares, each with a side of 7 centimeters long. So that would mean any of these different side lengths here of any of the squares would be 7 inches long. Okay, now if I also call this one 7 inches long here, you might be able to think back into geometry and realize that we've got a 45, 45, 90 triangle here. And the special relationship on that, or you could do Pythagorean theorem to find this missing side here, you would find it to be 7 square root of 2. Right? Now this problem wants to know the perimeter of the window. So if each one of these blue shaded sections are 7 square root of 2, right, what we find ourselves working with here is we've got each one is 7 square root of 2. And how many do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. So 56 square root of 2 would be the perimeter, because of the 7 times the 8 there, of this scenario. All right, and this is, like I was mentioned, that architects will use this a lot. If you're laying tile in instances like this, where you've got the squares, maybe you're making a diamond pattern with the squares turned sideways, you could find the perimeter of this shape very easily. It's 56 times square root of 2. And then, depending on what type of situation you're finding yourselves in the architecture, you could take that perimeter and do different other components with it. But just showing us here one quick example on how, being able to multiply numbers and radicals could come into play.